Good morning, ladies and gentlemen. Welcome to the second session of our Expert On webinar series on reducing carbon emission in cement and concrete. I am your host in English and Chinese to English interpreter Jia Li. For better efficiency, we will use simultaneous translation, which means there will be a channel in English and a channel in Chinese. For our Chinese audience, the webinar will be broadcasted live via Sino platform and automatically chosen Chinese. For audience from EU and UK, you're using Zoom, and please choose the English channel by using the translation button on the right bottom corner. Carbon neutrality or net zero is now a relatively familiar topic. This webinar aims at providing a platform for researchers in China and UK and EU to share their learning and experiences. The webinar series is hosted by China Ecological Building Material Association, Arcus and Callisto Consulting, and Future Build. The Ecological Building Material Association is a branch of the China Building Material Federation. Their work relies on the technical strength of the Environmental Material Science research team of the China Building Material Academy and the State Key Laboratory of Green Building Materials. They focus on promoting green, low carbon, ecological, and healthy building materials, products, and technologies, and its industry development. We've lined up today's presentation in a way that makes understanding easier. So today's expert speakers and their topics are Juan Perez Papi on overview of potential cement substitutes, Dr. Tongbo Sui on China's low carbon cement overview and development, Professor Lin Wang on how R&D of concrete can help further low carbon agenda, and Dr. Sayed Ghaffar on low carbon concrete for modern methods of construction. After the experts' presentations, we will summarize questions from both platforms and ask our experts. Audience on Zoom, please use the chat box to post your comments and questions. At the same time, you can scan the QR code on top to join our WeChat group, on the bottom to our LinkedIn group to continue the discussion. Last but not least, this webinar series is sponsored by Beijing Huangsha Building Material Technology. Beijing Huangsha is a high-tech light asset enterprise with international vision that provides services in technology R&D, intellectual property rights, and integrated systematic solutions in the field of carbon neutrality, circular economy, and solid waste building materials. Now let's watch today's first presentation from Dr. Juan Perez Papi, overview of potential cement substitutes.
Good morning, good afternoon, and thank you very much for inviting me to this webinar between UK and China. My name is Juan Perez Papi. I am a lecturer at the University of Salford, and I'm going to make a presentation about a review of cement substitutes. We can see that cement and concrete accounts for 7–8% of world annual CO2 emissions, and it is a lot. Therefore, the solution that we have is to see alternatives for cement in which we can reduce these CO2 emissions that are produced. So, well, when we are having considerations about cement replacement, there are different aspects that we shouldn't forget. For example, we should find materials that are going to bring a similar performance. So they behave similarly to cement. If not, there is no purpose. It is not worth replacing. Additionally, if we want to reduce CO2 emissions, well, we need to find these materials with low embedded carbon. So in that case, it is very important to find materials which carbon emissions, which embedded carbon footprint is lower than cement. We need to find materials that are going to bring similar durability, that our buildings are not damaged because of this change. And of course, there shouldn't be any reaction with other materials, otherwise we are jeopardizing our construction. Another important factor is that they should be cost efficient. So there should be a good economic balance with it. And of course, we need to find resources that are not scarce, that are not that are renewable, or that we can perfectly have a good source of them, and we can perfectly exploit them without any problems in future. And finally, another important element that we need to think is about the supply chain. So how are we going to process these materials and introduce them in the market for the construction industry to be used, right? So it is a lot of things that we need to consider if we want to make this replacement correctly. So what solutions that we have commonly used until now, it is to make partial replacement. And this partial replacement, we have found, for example, two very good materials that can perform similarly. And it is fly ash and blast furnace slag. So for example, talking about fly ash, what we need to think is about the origin of this fly ash. Most of it, we know that we burn coal, perhaps one of the most relevant sources of energy that we have nowadays in the world, it is coal. So when we burn it in power stations, for example, what we produce is two different types of ash. One is fly ash. It is the small particles that goes up, right? That are perfectly burned and they go up. And we've got furnace bottom ash. So it is thicker, it is heavier, and it is deposited at the bottom of the furnace. So you can see that, for example, fly ash is about 80% of the total waste that we have from coal burning, and furnace bottom ash, it is 20%. So what we are going to have with fly ash is that we are going to collect it with electrostatic precipitators so that we don't pollute the atmosphere. And we are going to see the possibility to use it as a pozzolanic material. So what we are going to look at is materials with pozzolanic characteristics so that they can perform similarly to cement. So characteristics that we need for this fly ash, it is mainly fineness. So it is very important, the fineness of this material, because this way it will be able to combine properly. The microstructure is also important, and the chemical composition. So with these values, it is the way that we are going to classify the fly ash that we are going to get, and to see if it is right to combine for a cement replacement. We are going to have very different types of fly ash. What we are going to find is the right chemical composition in this material so that the reactions that we get with cement as partial replacement, the reactions that we have with cement are correct, and we get a good replacement for this material. So important things, it is that fly ash has pozzolanic characteristics. This is very good, right? So in that case, what happens is that it combines with lime that it is in cement, and it forms hydrates. And with it, it is the way that they create these links as the binder. What happens is that as this pozzolanic, this fly ash combines with lime, what happens is that it removes this lime from cement, and it increases strength and durability. So what we are going to get with this combination is even a better performance than with only cement. Despite that, we have also some problems. For example, we can have problems with carbonation or with resistivity. At some point, they can be good, but in other cases, it is not so good. So for example, with carbonation, what we get is that concrete becomes brittle. So, but it increases strength, right? So we have good and bad performances there. And another characteristic that we have with this process, it is that the resistivity of the material, the resistivity of concrete increases, resistivity increases, and then it avoids corrosion, for example, corrosion of the concrete, so not to be carbonated, and also corrosion for the reinforced steel that is inside. We should be aware that we can't replace everything, so the maximum percentage that we can think of replacement is about 40%. More than 40%, what happens is that there isn't enough lime to combine. So in that case, the rest that is not combined doesn't work with these pozzolanic characteristics, and therefore it is an inner part. So in this case, what happens is that the combination is not right, and then it doesn't work as a binder. Well, what happens with a blast furnace slag? Well, blast furnace slag, it comes from iron or steel manufacturing in blast furnaces. And this is waste that we have. So this is all impurities that we have in the mix, in the iron mix on surface, right? And then it's eliminated. All these impurities are eliminated so that iron purity is right to be used in industry and later to be manufactured. So what we get with this slag at the end, it is waste. So it is exactly the same as the fly ash. The only thing is that we use them as a byproduct and we obtain a value, an added value to this material. So with slag, we can obtain this material in 3 different ways. One is, the first one, it is leaving it to cool in air, right? So just to cool outside, or we can mix it with water, and what we obtain is a process that is called as foaming, right? So in these 2 ones, what we have is that this slag, it doesn't get these characteristics to be a reactive material, and therefore they cannot replace cement. So in these cases, what they are going to be used, it is as aggregates, right? There is a third treatment, and it is with high pressure jets, and it is what we obtain as granulation. So in this way, it is in which we obtain these hydraulic characteristics, pozzolanic characteristics, and we grind this material and we obtain what we call as ground blast furnace slag. Then it is mixed with cement, and perfectly it works as a replacement for cement. So characteristics of this material. Well, this material is very slowly hydrated in contact with water. It performs differently to fly ash, right? So fly ash combines directly with cement. This material doesn't. This material performs in different way. Okay, so what happens is that this material is activated with lime. So it means that it starts this reaction, and it can harden in itself inside the mix, right? And it is the way that it gets this similar performance as cement. What happens with this material is that it gets a lower early strength. So in the first days, we are not going to get the proper strength as cement, right? But as long as time passes by, what we get in longer ages, what we get is higher strength than even cement, right? So for example, after 1 year, we can perfectly get a higher strength than with cement only. And another important characteristic that we have with this material is that it is sulfate resistant. So we are going to make specific special concrete in which it should be sulfate resistant. This is a good material as an addition that we can use. Well, here we can see a comparison between different concrete mixes in which we are using fly ash or slag, right? And you can see how CO2 emissions are reduced in these concrete mixes. So you can see that perfectly, according to the addition of fly ash and slag, what we are going to do is to reduce the carbon emissions that we release with this mix. Here, for example, what I am showing is a table with the European cement types. So we can see that we are using different cements, and in these cements, it is regulated the way in which they are mixed, and we are using fly ash and slag as additions. So what they are doing is replacing part of cement. So for example, in CEM1, what we have 5% of additions, The rest, it is clinker, so it is 95% clinker. So the purity that we have with cement is high, and this 5%, it is replaced with other additions. In these additions, we are including fly ash and slag. We can see that we have composite cements. So for example, CEM2, there are two specific cements in which we have fly ash or slag, right? And we can have up to 35% of additions. And then we have also one specific CEM3, in which it is a blast furnace cement, so it is with slag. And what we have is higher percentage, higher proportions of this slag, so more than 35%. And we have also a CEM4, that it is a pozzolanic cement, in which we have up to 55% of pozzolanic additions. Pozzolanic additions, it is fly ash or slag. So any of them are pozzolanic additions. And in this case, at the end, we have also a CEM5, in which we have a combination of both, right? So it is specifically a combination of both. That is why we call it as composite. What happens with these types of cement is that they have different properties. So for example, if we want to make a sulfate resistant concrete, what we are going to use is a cement in which we have an addition, a high addition of slag or a high addition of fly ash. So what we are going to do is to give different properties according to the amount of material, the amount of additions that we are going to have in it. Also, it depends on, for example, the heat released in the mass. So for example, CEM3 and 4, they are low value heat release. So this is very important if we are going to do mass concrete, for example, for big infrastructures like dams or things like that. So depending on this, we are going to create different types of cements with different behavior, with different performance. Well, let's go ahead. Let's see what happens with other type of solutions that we can find to replace cement. And it is what we call as alkali activated concrete. So here what we have is that we replace cement completely. We are not using cement anymore. So here what we are using is mainly alumina-rich or reactive silica materials, right? And it is what we have as fly ash and slag, right? So we are going to use 100% of them without any cement, plus an activator. So what we are going to do is to find an activator that will activate, that will react with these materials, and they create a binder for this concrete, right? So what type of activators can we find? Well, it is more a chemical aspect, what we are going to see here, and it is, for example, working with caustic alkalis. So it is sodium or potassium hydroxides, sodium carbonate, for example. We can also use silicate salts. It is, for example, sodium or potassium silicates, or we are going to use, for example, non-silicate salts, weak acids, for example, sodium phosphate. So any of them, it is, they can be used as activators to react with fly ash or slag, right? Of course, not all of them react. So there are specific combinations in which we are going to get better or worse characteristics, or we are going to get different types of reactions with these materials, with different performances. Important thing of this, well, the important thing is that, for example, if we compare the CO2 emissions that we have to produce 1 kilogram of cement, we can see that in this case, the CO2 emissions that we have are very much reduced. So we are reducing about 5–6% the total CO2 emissions that we have with cement. So it is a very good solution to replace cement. Okay, so that's why alkali activated solutions, it is what it is now very much explored and developed to see what type of materials and what type of solutions we can implement. And another important aspect is that it is 20 to 30% cheaper than Portland concrete. So you can see that we have a very good solution environmentally and economically. So in this case, alkali activated concrete is a very good niche to explore if we are thinking about cement replacement. But of course, it is not so good, right? So we have problems as well. We have many problems, right? So we need to think about parameters, for example, that can affect this reaction. And it depends, for example, in the type of activator that we are using. So for example, if we are using slag, in this case, probably the best activator that we can have is sodium silicate. If we are making the combination of fly ash and slag, perhaps it is better with sodium hydroxide. So we need specific solutions for specific types of fly ash and specific types of slag. So there is no only one solution and no one composition. We need to explore specifically for the type of fly ash, for the composition, chemical composition that we have in the fly ash and in the slag, and to see what activator we can use in each case. And of course, it is also about the proportions that we are going to use, right? So we need to calculate the modulus, the molar combination that we are going to have, and all these parameters that are not easy to identify. It is also important to identify the nature of the activator. It can be dry or it can be wet. We are not working now with a combination of water. So water doesn't have anything to do now. Water is not working with cement, it's not hydrating anything. The only thing that we have with water it is that it adds workability to the mass, but it is not reacting. So water is not relevant in this mix. So what we have to see is how we are going to get the best solution with the activator, if it could be dry or wet, and we will have different reactions with it. The activator modulus, it is the relationship that we have between acid components and basic components. So you can see that there is silica, for example, this is acid, and when we are talking about sodium or potassium, it is basic. So in this case, or alkaline. So in this case, what we are looking at is at the relationship of this composition. And according to it, we will calculate this activator modulus, and we will see the reaction that we can obtain with them. It is also important to identify fineness of fly ash or slag. Depending on this fineness, the reaction will be better or not so good. Also, depending on the concentration, it is the concentration that we have in the activator of the different components that we can have. So for example, one optimum solution that we can have with this activator, it is to have between 3 and 5% of sodium concentration in the activator, and it will help to make this combination much better, this reaction much better. And another parameter that we need to identify, it is the curing temperature. We have a problem with fly ash, and it is that if we want to make this reaction happen, what we need is to add heat. So if we don't have this possibility, this reaction will not happen. So for example, with fly ash, to make this concrete, we need to add heat at least during 24 hours between 60 to 80 degrees, right? It reduces then the possibilities to use this on site. So if we need to cure with temperature, this is not possible on site. And then the possibilities of alkali activated concrete is reduced probably to work off-site, to work with precast solutions or modular solutions. Otherwise, to concrete a floor, for example, is not possible with this solution. So we need to work off-site. And we have another problem behind, and it is the resource availability. When we think about fly ash, we can see that the market is growing. So you can see here, for example, that the global market for fly ash is growing from 3.5 billion in 2020 to 4.9 billion in 2027. And if we can see the growth rate that we are having with these markets, you can see that the world is growing to 4.9%, this market, and China is growing to 7.6%. So it is nearly twice. So we can see that the growth rate to use these byproducts is growing hugely. And there is a problem that these are byproducts. This is not a material that we produce commonly. Besides, we need to think about the global primary energy consumption that we have in the world by source. So we can see that oil is the first primary energy that we consume, and the second it is coal. So the resources that we can have from this burning, from coal burning, are many, of course. So at the moment, we don't have any problem. We don't have scarcity of these materials, but there is a limit. There is a limit with this consumption that we have for primary energy. And we need to think also another thing, and it is that coal is a very pollutant energy, a very pollutant fossil energy. So for this reason, what's happening in the world is that whereas the different sources of energy are increasing, we can see that the use of coal globally is reducing. So in future, we are going to use less coal and we will have less resources available, less byproducts available for this. So the consumption of cement will never be replaced with fly ash or slag because it's impossible, because we don't have these resources. So we need to find other resources. We need to find other solutions apart from fly ash and slag, right? Because they are not the solution. There should be more solutions because of this. Therefore, what we need to think is how we can produce other materials, how we can manufacture other materials that are lower carbon emissions, with lower carbon emissions, and we can have also these porcelainic characteristics. And it is when we think about metakaolin. So with metakaolin, what we do is the calcination of kaolin clay. And what we obtain with this calcination is a porcelainic material. So we are getting a similar, a material with similar characteristics to cement. And with this material, we can partially replace cement in mortars and concrete. So we cannot replace cement totally with it because we need this material to react with cement, but we can replace it partially. We need to think that this is not a byproduct. So this is not waste. So what we have is to produce it. And then if we want to produce it, what we are going to do is to use energy to produce it. So in this case, we are consuming energy. So it is not a zero carbon emission, a zero carbon solution, for example. In this case, we are consuming energy. What happens is that the energy consumption that we make is lower than producing cement. So we are getting a lower carbon footprint with this metakaolin. So what is kaolin? Kaolin is a very pure clay. So what we have a lot of kaolin sources in China. So for example, Chinese clay is with very high content of kaolinite. And this is the basis of metakaolin, right? So what we do with kaolin is to calcinate it at about 600, 800 degrees. And we obtain the transformations, as we can see in the formula below. We can get these transformations to obtain metakaolin. At the end, what we are doing is to break this molecule and we release water, right? And we change this molecule and we obtain metakaolin this way. Okay, so this is, it is easy. It is not a complicated solution, right? So the only thing is that we need to add energy to this element. Despite that, we should think that, for example, when we produce cement, we are going to double this temperature. So we are working with about 1,400, 1,600 degrees. And here with metakaolin, we are calcinating at 600, 800. So it is quite less energy what we are using. Well, what happens with this material? Well, we are not using this material much. This market is growing, okay? We need to think that this is something that it is being introduced in the market now, okay? And with this metakaolin, for example, you can see the differences that we have in the demand between 2020 and 2027. So you can see that the market, the expectations is to double this market in the following 7 years, right? So we can have a growth of this market of about 5.4% rate, right? So progressively annually, it will grow about 5.4%, right? But currently, there is not much consumption of this material. Okay, so perhaps it is something to think about, right? And see what possibilities we have to get a bigger manufacturing process for this metakaolin and to grow this market so that we can perfectly use with cement. More solutions. Well, perhaps these are the best solutions that we could have for now, okay? But there are more. We are exploring more elements. And one thing is about potash. So what happens with bottom ash? Well, with bottom ash, what we are doing is that we are calcinating other materials. So for example, if you remember with coal, we have fly ash and bottom ash. So this 20% that we have at the bottom, we are not using it anywhere. So probably it will go to landfill, or we can use it as aggregates. So in this case, what we can try to find is if we can have any pozzolanic characteristics, right? Exactly the same with wood, right? So we can perfectly calcinate or burn wood, right? And we obtain also bottom ash. Waste, exactly the same. So we have municipal waste, for example, we have biomass waste that is calcinated, and we obtain also this bottom ash. Well, the thing is, how can we obtain pozzolanic characteristics with this? Well, it is not easy, right? So bottom ash is, is a different world. So these pozzolanic characteristics will depend very much on the content of different components. For example, the most important components that we have, it is silicium, aluminum, iron, and calcium. So the bigger amount of calcium that we have, the worst performance that we obtain. And the inverse, the highest percentage of silicium and aluminum and iron as well, we will obtain better pozzolanic characteristics, right? So depending on this proportion, we will see what degree of pozzolanic performance we can obtain, right? There are some good uses. I will explain one example now, okay? But in general, it is difficult to find them. Important things, important problems that we can have, additional problems that we can have. Well, for example, if we are working with municipal waste, we can have problems with heavy metals. Or if we are working with construction and demolition waste, be careful. We should be careful with heavy metals contamination, right? Because in that case, we can't use this in concrete, right? Because it will damage the whole mass, right? Because it is contaminating, so it is not healthy. So we should avoid that. We have another problem, it is grinding, right? So grinding this bottom ash, many times it is not cost effective. And the thing is that at the end, we have better solutions that we can have with this bottom ash, for example, as fertilizers or any other type of additions, for example, aggregates or similar. And many times we try to find the most cost-effective solution for it, right? But well, it is something to explore, right? So if we have this resource, it is good to explore it and see the feasibility of these possibilities. One interesting example, it is the rice husk ash, right? And what happens is that it is a very important source in specific countries. For example, China, they are very good manufacturers with rice. So the rice production is huge. And this could be a good solution to obtain a pozzolanic material, right? So what we do with rice husk ash, it is to burn it under controlled combustion conditions. So it is about 500, 700 degrees for 1 hour. And when we do this way, we obtain ash with pozzolanic characteristics. So this ash, it is mainly amorphous silica. So if you remember silicium, right, with a microporous structure. So what happens with it is that it has a very porous material with pozzolanic characteristics. So the possibilities that we have to react are very good. And then the combination with cement are also very good, and they collaborate with cement. So one thing it is grinding. So with this material, it is not so good to grind it completely to a very high fineness, mainly because we have this microporous structure, and if we grind it, we are going to break it. And if we break it, we destroy these pozzolanic characteristics. So fineness in this case should be kept not so small, okay? And we should consider also the need of additional water. We need to think that this microporous structure porosity is increased, and it will require additional water. So with this, right, we need to play and find the right mix with cement. Well, here it is a table, and it is almost to conclude. Here we can have different materials. We've got materials that we have already talked: cement, lime, hydrated lime, metakaolin, rice husk ash, and fly ash, and the energy that is required to obtain these materials. So you can see that the energy for cement is high, And if you compare with the energy that is demanded for the rest of materials, it decreases, right? And of course, the CO2 emissions, the embodied CO2 emissions are also reduced. Finally, one solution that doesn't have anything to do with pozzolanic reactions, it is to work with polymers. So what we have is the possibility to mix cement with polymers, right? And these polymers can help as a binder, can help cement and work it as a binder. So we know nowadays that that we have a lot of issues with plastic waste. So this could be one solution that that we can discuss, and we can see in what way this plastic waste could be mixed in the concrete, right? So by heat, for example, we can mix in small chipping elements. We can grind it, and these chips can be mixed as an aggregate, and then with heat we can melt them partially inside and increase the binding or the bound of the materials. Another possibility it is to work with any type of dissolution in which these plastics are diluted and mixed with the mix, with the concrete mix, and then they solidify inside. Here we have problems. And we have a long discussion about if it is a good or a bad solution, mainly for the two reasons. One is about microplastics. What happens with microplastics? Nowadays we have a lot of problems, or we have discovered a lot of problems, because these microplastics are affecting the food chain that we have, and these microplastics are also being inside our bodies, right? So we should be very careful with microplastics and measure it. So if we make this solution, we don't know if this will affect in future and create more microplastics that are released from this concrete when it is washed. We don't know, right? So it is something we should be careful. And the other thing, it is about recyclability. So imagine that this concrete with these polymers is created, and in 50, 100 years, it is demolished, it is crushed again, and in the mix, there is plastic, there is aggregates, and we don't know how to separate them. So we don't know if with this solution, we are creating problems in future that we don't know how to solve them. Nowadays, we don't know how to solve them either, right? So it is something that we need to think about and be careful with this. So at the end, we need to be cautious with this solution about plastic waste, and to be used in concrete. And another solution, it is to work with biopolymers. What happens with biopolymers, it is that they are natural materials, right? So they are from mainly plants or organic compounds. For example, we can think about other binders that have been used during history. For example, we can think about grease, we can think about blood, and other materials, other biopolymers that were used during history in our construction tradition. In this case, what happens with these biopolymers, it is that we can perfectly explore the possibilities to use them as binders, right? And perhaps to help the characteristics of concrete, and also to help the characteristics of cement, to improve these characteristics. For example, we can think about nopal. Here, for example, this picture is about nopal. So with nopal perfectly, we can use the nopal juice, and we can mix it in the concrete mix, and it helps, for example, waterproof, and at some point it can also improve strength of the mix, right? So we can think that these solutions that form part of our construction tradition, that they were used in the past, perhaps we can think about how to reintroduce them in the system and to find solution that could be very useful for us nowadays. And well, finally, I wanted to conclude mainly to see that that we have seen different low carbon solutions for cement. We have seen different replacement, different materials, byproducts coming from waste, new generation materials, and also what we need to think is that there are a lot of solutions currently that are being introduced in the market. So we can think about possibilities that can be developed perfectly, and we should explore the possibilities that we have around, that we have locally, and perhaps we can find products, we can find byproducts or waste from different industries that can be byproducts, and we can see how to improve the value chain of them and reintroduce in the manufacturing process for cement. So it is important to find the challenges in which we can adapt technology, and also that they should be cost efficient. So solutions that can also work economically for us in the market. It is also important to think about resource exploitation, to think about the source of this material and the availability for that. And not only availability, but also how we are going to exploit it. And of course, as I said, there are many possibilities and niches to explore. So in this case, for example, thinking about circular economy and value chain. So we can think about perhaps solutions that we can have with construction and demolition waste. So there are many products there that could be transformed and reintroduced in cement manufacturing, for example. There are also other byproducts that can come from different industries and can be transformed and reintroduced as well as binders. We need to think about how we can optimize the processes, how we can improve the way that we are going to work with these materials, and to optimize the characteristics that we are going to obtain. As I said before, we need to think about particular solutions for specific problems. So probably we have solutions in front of us that are near us, and we don't need to look for something further. So perhaps with the resources that we have locally, probably we can find solutions that can work correctly for our problem. And then, of course, we have to see how to develop the market with standards, certification, and processes that can give guarantee, that can ensure, that can give the quality assurance that we need for all this. And finally, I would like to thank you very much for your attention for all this time, and I hope that that it was helpful for you, this presentation. If you have any questions or you have any comments that you would like to make, we will have a discussion now after this presentation.
Okay, thanks a lot, Juan. Now I would like to take this opportunity to introduce our important partner, GCCA. GCCA, the Global Cement and Concrete Association, is an industry initiative led by CEOs of global cement and concrete sector. Their vision is to create a world where concrete supports global sustainable economy, social and environmental development priorities, and where it is valued as an essential material to deliver a sustainable future for the built environment. Until last year, GCCA members cover up to 40% of global cement production and are expecting to reach over 75% in the recent years. Their members include the well-known LafargeHolcim, Cemex, Heidelberg, and Sinoma, and so on. So please see a video from GCCA on their climate ambition.
Concrete is strong, durable, sustainable, affordable, renewable, beautiful, and a resilient part of our world. It is the foundation of many human stories, past, present, and future. Now, as the world faces unprecedented challenges, concrete has a vital part to play in our recovery. But some things need to change. More than ever, our planet needs cleaner, greener infrastructure. And as an industry, we have the responsibility to enhance its environmental footprint and accelerate progress. As the world's most sustainable building product, concrete is ready to meet this challenge. Ready to build a safer and more sustainable world. And ready to commit by delivering carbon neutral concrete for the world of tomorrow.
Okay, so GCCA welcomes new members to join, and we will put the GCCA website in the comment area, and more details will be published in the Arcus and Callisto official account. Please stay tuned. Audience on Zoom, please use the chat box to post questions and comments for the Q&A session. And you can also scan the QR code on the top to join our WeChat group, or on the bottom for our LinkedIn group to continue the discussion. And now let's watch presentation from Dr. Tongbo Sui on China's low carbon cement overview and development.
谢谢主持，尊敬的各位专家代表，大家好。首先非常感谢中英建筑建材行业碳中和主题论坛组织者的邀请，非常有幸的与各位专家代表一起来交流，共同探讨碳中和这样一个全球热点的主题。今天我的报告的题目是中国低碳水泥技术的现状与发展展望。报告总共分为以下4个部分。首先是中国水泥工业的发展的简况。波特兰水泥自1824年诞生至今，将近200年的历程，已经成为人类社会主要的建筑材料。以水泥为交易材料的混凝土也已经成为社会第2大商品。未来的需求分析表明，到2050年，波特兰水泥在未来全球总体的需求仍然呈现了一个上升的趋势。当然，这样一个上升的趋势不是发生在 OECD 经济发达的国家，也不是发生在中国，而主要是发生在印度以及其他的发展中国家。这个从图里边可以清楚的显现。目前全球水泥二氧化碳的排放占全球总排放的7%。那有个机构形象的比喻，如果将混凝土行业作为一个国家排序的话，那么混凝土的碳排放位居全球第3。中国目前是世界水泥混凝土生产消费最大的国家，那么它的生产消费量占全球的50%以上。自2014年，我们可以从图中可以看到，中国水泥的产量达到最高峰以后，一直是稳中有降。当然，中国水泥工业那么还具有以下的特点：一是不断提高的能效水平，这可以近5年中国水泥熟料综合能耗的水平的变化可以清楚的显现。第二是高的熟料替代，从右图那么给出了过去的15年当中，那么中国水泥熟料系数的变化。你可以看出，近10年中国水泥一直熟料系数处于较低的水平。那么近5年虽然呢有从0.56上升到0.66这样的一个趋势，但总体仍处于一个国际低位的水平。第3个呢是余热发电的广泛利用，5000吨以上的水泥窑，那么几乎呢100%的采用了余热发电技术，这也是中国的特色之一。第4是协同处置方兴未艾，那么这主要呢是主要是处置的生化垃圾，那么尘石、污泥以及危险废物。那么目前呢已经有很好的案例，比如江苏的溧阳、河北的武安等。那么由于采用了水泥窑的协同处置，使得尘石垃圾日产日清，成为绿色无废城市发展的典范。下面汇报第2部分，中国水泥工业碳减排、碳中和技术潜力的分析。首先回顾一下国际水泥混凝土行业低碳的路线图。那么这里简单的列举的就有10几个国际制定的路线图，其中呢涉及到了全球、区域、国家、公司等多个层次。全球第1个水泥行业低碳技术路线图呢是在2009年 由 IEA 国际能源署和 CSI 水泥可持续发展组织联合发布。在2018年呢，当然又有了更新的一版。就在昨天呢，GCC 全球水泥混凝土协会也发布了水泥混凝土行业净零排放混凝土路线图。中国建材、中材国际也积极参与了 GCC 路线图的制定。以 IEA 水泥低碳技术路线图为例，那么主要的技术路线包括提高能源效率、替代燃料、低碳水泥以及碳普及与封存，也就是咱这说的这个 CCUS。水泥作为难减排的行业 ，CCUS 的应用是必不可少的。也就是说，除了水泥行业自身的技术主动减排以外，对 CCS 的依赖度高达48%，才有可能实现水泥行业自身的这个净零排放。中国水泥工业减碳脱碳技术的潜力分析呢，那么所涉及到的4个技术路线图的选择以及潜力分析呢，与 IEA 的这个刚才的这个分析呢，基本是相同的。那么如果将水泥产业链去延伸到混凝土建筑技术的话，那么通过混凝土质量的优化提升，那么建筑环境以及混凝土再碳化等一些因素呢，那么对于 CCS 的依赖度呢，将显著的降低，大致可以降低到1/3的水平。下面就简单的介绍了一下中国水泥工业减碳脱碳技术途径的一些具体的情况。第一个呢，是目前最佳的实用低碳技术的方案，这个包括能效提高技术，刚才已经谈到过了，熟料的烧成热毫和综合粉末电毫，根据现有的技术指标，目前呢，中国呢已经达到了国际先进或者领先的水平。那么，除非出现颠覆性技术，未来在这个方向，利用该技术途径减排的这个潜力不大。刚才说了5%左右。那么，替代原燃料技术，那么这个里边呢，主要包括了水泥生产钙质原料的替代，以及水泥窑协同处置各种废物技术及非碳水盐钙质原料的。目前主要利用的是电商，其他呢尚没有采用这种替代的燃料的比例，也目前呢只有大约2%，未来减排的潜力比较大。熟料的替代技术刚才已经谈过了，也就是说利用矿渣、粉明灰以及火山灰质混合材等来去替代熟料，而不对水泥的质量和性能呢产生不利的影响。中国水泥行业在这个技术路线上应该说发展的很快，在国际上目前来说，中国水泥平均的熟料系数也是处于一个低位的水平，去年是0.66这样的一个水平。关于煅烧粘土的技术呢，在目前呢是国际的热点，后面呢有一张片子专门介绍。余热发电刚才也谈过了，那么这是典型的中国特色的技术。那么作为行业普遍采用的技术呢，未来在这个方向，那么它提升的潜力也不大。低碳熟料水泥技术，那么这是典型的中国特色的技术和产品。那么包括比如说硫氯酸盐水泥、高倍率的水泥、贝利特硫氯酸盐水泥等等。那么这些产品呢，目前尽管产量不大，最大的也就上100万吨，但随着未来市场的不断的开拓，节能减排的潜力，它们将不断的提高。第二个方面呢，是未来主要的脱碳技术方案，这个就是刚才所提到过 CCUS 的技术呢，主要包括燃烧后的普及提纯以及燃烧过程的自负极，其中包括全氧燃烧、间接加热、碳钙循环等等。那么这是全球目前研究的国际的热点。我们的同行拉豪、海德堡、CLH、CMAX 等，他们都已经在大力的投入。目前 CCUS 相关的几条技术路线都已经打通，但是面临了2大方面的挑战。第一是一次性的投资水平高，碳普及利用成本居高不下的难题；第二是普及二氧化碳如何的利用和封存的问题。未来发展的关键是不断的创新，提升技术经济可行性，加强政策支持与引导， 推动市场需求与生产规模的扩大。借此机会呢，也介绍一下中国水泥 CCUS 这样一个发展的一个基本的情况。第一呢是2014年台泥的钙循环结合生物制造技术的示范。第二个呢是2018年海螺水泥5万吨的燃烧后普及的提纯示范项目。第三是仲裁国际开发的全氧燃烧自负极提纯技术。这个时候呢是可以通过这个技术方案呢，可以将烟气中的二氧化碳浓度从30%左右负极到75%以上，那么从而使提纯技术从燃烧后普及技术的化学吸收改为高浓度下的物理吸附，这样可以降低 CCUS 的一次性的投资和二氧化碳普及的运行成本。在“十四五”期间，我们将开展示范项目，主要是5到10万吨的年普及量的规模示范，以及全系统2000到2500吨的工业示范。第四是关于二氧化碳矿化利用技术，在这个方面，仲裁国际已经成功设计建设了利用窑为废气制备年产5万吨 PPC 轻质碳酸钡的这样的一个项目，设计和利用窑为废气与电势差反应制备年产5万到10万吨的 PCC 轻质碳酸钙的项目。另外一个就是浙江大学与企业合作呢，成功开展了利用二氧化碳养护制备钢渣混凝土砖的这样一个工业示范。第三部分，中国水泥工业低碳水泥的类评。首先是关于低碳水泥。那么从整体而言，可以认为中国水泥本身就是低碳水泥，原因大家已经清楚。由于中国水泥比例当中的高比例的塑料替代，我们以2020年为例的话，中国水泥的产量是23.8亿吨，输料15.8亿吨，由此得到的塑料系数是0.66。那么如果将单位的二氧化碳直接排放强度，单位塑料的二氧化碳直接排放强度，那么按照0.85吨二氧化碳每吨塑料来计算的话，那么将两者相乘，就可以快速的估算单位水泥二氧化碳直接排放强度为0.56吨二氧化碳每吨水泥。借此呢，机会也介绍一下仲裁国际负责承担的“13五”的重点项目——煅烧粘土低碳水泥的技术。那么这个呢，也是国际上研发的热点之一 ，LC3 水泥。那其主要的特点是利用煅烧粘土与石灰石复合等大比例的替代塑料，在塑料系数0.5时 ，LC3 水泥的28天的强度可以与纯硅酸水泥相当，而且耐久性更优。本项目的另外一个特色是开发高效节能的煅烧技术，整个的煅烧过程呢，从入料到烧成在1分钟之内完成。照片所示的，那么是本项目的成果的一个示范应用。2019年1月，那么项目成功的在悬浮煅烧生产线开展了日产600吨的煅烧粘土的工业实验。实验结果表明呢，该系统经过标定煅烧的热耗是457千卡每公斤，较回转窑系统呢要降低了42.8%。那么核算新型低碳水泥二氧化碳的直接排放量较 P 降低40%，较 PO 降低20%以上。高效节能悬浮煅烧系统呢，也具有良好的普适性，可以不仅适合于煅烧粘土，也可以适合于煅烧其他非结构矿，比如说煅烧氧化镁、煅烧氧化钙等等。仲裁国际呢，目前呢已经建成了2个在国内的一个悬浮煅烧项目，另外新签订了2个合同，一个是国内，一个是国外的。中国低碳水泥的另外一个特色是低碳塑料水泥。那么从表中给出呢，大家可以看到低碳塑料水泥的组成和节能减排的水平。那么 CSA 琉璃酸水泥是从上个世纪呢70到80年代投入的工业生产应用。 HBC 活性贝利特水泥呢，是上个世纪呢90年代开发并投入工业生产应用。BCSA 作为最近的5到10年开发的产品，那么由于尚未制定国家的标准，工业生产应用呢尚处于一个初级阶段。这两个图呢，给出了3种低碳水泥与波特兰水泥强度的一个对比的这个实验。我们可以看到，这些水泥是各具特色。CSA 的特色是快硬高强 ，BCSA 的这个特色呢，那么它是具备了 CSA 的基本特征，但呢，它的配料当中呢，铝含量比较低，因而原材料可获得性好，成本更低。HBC 的特色呢是低热高强，以及它优越的抵御混凝土温度应力的能力。这些水泥的性能呢，各具特色也决定了它们的用途。CSA 主要用于快速施工、快速抢修、复温施工以及混凝土的制品制备，比如说 GRC 墙板、预应力管道等等。那么复温应用的典型的案例呢，是在85年应用于南极的长城站的建设。HBC 呢，应用的主要的领域是在大体积混凝土方面。那么第一个成功的应用案例是世界最大的三峡大坝3期工程，目前呢已经为水电行业呢所广泛采用，整坝使用。典型的工程案例，那么最近是建成的这个白河滩电站，也是全世界第2大水电工程，整坝采用了混凝土贝利特水泥，没有产生温度裂缝，也改写了水工行业无坝不裂的历史。最后发展展望，总之，中国水泥工业实现碳减排、碳中和，挑战与机遇并存，任重道远，需要多种技术途径，需要不断的创新，需要建立新的循环经济产业链、生态链、价值链。CCUS 呢是水泥工业净零排放的关键技术，有望从2025到2030年以后开始规模化的部署，完成双碳目标。没有捷径，只有坚持创新、合作共赢，也需要我们立即行动。从目前开始到2060年，中国水泥工业实行碳中和分为3个基本阶段。第一个是10年的碳达峰期，15年的碳中和关键期，以及15年的碳中和决胜期。所采用的技术路线，那么在前面的报告中已经介绍过，不一一说明。这图片当中展示的左边是中材国际水泥绿色制造技术在国内外建设的典型工程案例，包括改变水泥工厂形象的类似于社区建设的生产线，以及水泥微废协同处置智能生产线。右面是北京宝贵10亿科技的作品，从吊灯到仿石制品都是用低碳水泥制作的，这些都是水泥工业创新引领未来的典型案例。让我们共同努力，合作共赢，建设未来人类命运的共同体。谢谢大家。
So that's all from Professor Sui. Now I would like to take this opportunity to introduce Arcus and Callisto Consulting to you. Arcus and Callisto is an international consultancy based in London, England. The company has its team in London, UK, Beijing, and Shenzhen in China. ANC is committed to promoting technology transfer and learning exchanges in the construction and building material industry between China and UK. Core services include market development, agency introduction service, translation, online, offline training services, and community activities, etc. Please scan for our official WeChat and LinkedIn account, as well as visit our website online. Audience on Zoom, please again use the chat box to post questions and comments for the Q&A session. And you can also scan the QR code on top to join our WeChat group or the bottom for our LinkedIn group to continue the discussion. Now let's watch presentation from Professor Lin Wang on how R&D of concrete can help further low carbon agenda.
Hi， 各位专家、各位朋友们，大家好，我是中国建筑材料科学研究总院的王玲，非常高兴参加中英建筑建材碳中和论坛活动，和大家一起交流水泥混凝土减碳技术。先介绍一下我的工作，我的主要工作是在中国建材研究总院从事科研工作，也担任中国混凝土外加剂行业协会的秘书长，全国混凝土标委会的副秘书长，还参与 RILEM 2个技术委员会的一些工作。我的研究领域是混凝土耐久性和混凝土外加剂，刚刚完成一个为期4年的国家重点研发计划项目，极端环境下长寿命混凝土制备及应用技术。过去的近30年混凝土科研工作中间，针对高速铁路无杂轨道混凝土材料、多因素耦合作用下混凝土耐久性、束凝剂和喷射混凝土技术等方面集中开展过系统研究工作。十分高兴今天和大家在线上相识，希望以后能有机会见面，我们当面交流和合作。今天我的报告分3部分，先谈谈目前中国，特别是建材行业减碳行动的状况，再具体和大家分享混凝土行业减碳技术途径。碳减排是目前中国的最热词。自习主席在联合国大会发出双碳目标的承诺以后，碳减排已然成为一个国家行动。在“十四五”规划里面有约束性减排目标，未来5年中国单位 GDP 能源消耗降低 13.5%， 单位 GDP 二氧化碳排放降低 18%。 我认为实现碳达峰、碳中和的目标任务非常艰巨，在中国要发生一场广泛而深刻的经济社会系统性变革。目前中国政府各部门各行业都在思考如何实现减碳和碳捕集利用的一些技术途径。具体到建筑材料行业，中国建材联合会发布建材行业提前5年全面实现碳达峰，水泥行业提前7年实现碳达峰。中国水泥产量大，水泥碳排放因子高，所以任务最艰巨。水泥行业已经想出了很多好办法来促进碳减排，比如从煅烧工艺看，提出了替代燃料技术，提出了清洁能源利用技术。中国建材研究总院汪澜教授提出利用绿电、水解制氢，用氢能作为稳定热能代替燃料来煅烧水泥熟料。这个技术的优势是基本不改变现有水泥的生产工艺，且窑炉烟气中间二氧化碳浓度高，便于后续碳捕获和利用。从新品种水泥开发看水泥行业提出了低钙水泥熟料技术、低熟料水泥技术、无熟料水泥技术。近期国际上还有叫 LC3 水泥技术，这个是瑞士 EPFL 的 Karen 教授团队，他们近些年一直在研究和推广的一种新型水泥。它的组成是以煅烧粘土为主，加少量的石灰石和少量的水泥。它取3个组分，名字首字母称为 LC3 水泥。因为它的煅烧温度低，石灰石的用量少，可以降低40%的二氧化碳排放。中国混凝土行业也在积极思考如何减碳。中国是混凝土消耗大国，产量年年的增加，目前产量已经占到全世界总产量的60%。混凝土实现碳减排基本路径是减少混凝土中水泥的使用量， 和减少混凝土生产全过程的能源消耗。我建议呢，把目前的混凝土碳减排行动和以前开展过的资源节约、节能这些行动相结合，遵循呢成本效益原则，就是一项活动的收益必须大于它的成本。从组成上看，无论是预拌混凝土还是预制混凝土制品，现代混凝土都是由6大主份构成的。减碳呢，可以重点关注2个点位，减少对矿产资源，特别是天然矿产资源的使用，减少呢对煤化工和石化产品的消耗。从生产过程来看，步骤还是很多的，涉及到多种机械设备和运输过程，能耗很大。但是从一位材料研究者的角度来看，通过混凝土组成设计，很多生产的环节都可以实现能耗的下降。基于上述的分析呢，我总结提出4个混凝土减碳技术途径，让我们呢来逐一的讨论一下。首先是减碳路径1，优化混凝土原料组成和配比。具体呢，我列了5个措施。这里呢，我想重点谈谈第2点，矿物掺合料，和第4点，化学外加剂。先谈谈矿物掺合料。大量使用固废加工成水泥混凝土掺合料是中国混凝土减碳方面的先进经验。中国的高炉矿渣、粉煤灰、炉渣、钢渣和煤矸石年排放量都数亿吨，这些固废已经在水泥混凝土中实现了再利用，争取未来能够实现全利用，包括用于水泥混合材、混凝土掺合料和骨料等等。使用工业固废加工混凝土掺合料遇到的问题有：残余重金属含量的控制，粉煤灰中残余氨含量的控制，还有大量使用掺合料的话呢，需要考虑采取超细粉末、活性激发、添加能够调整粘度和早期强度的外加剂等等综合措施。使用工业废弃物加工混凝土掺合料，经济效益和减排效果都很突出。这里呢，我找到一个南京地铁工程的实例，14万立方的 C30 混凝土，原方案呢用 PO42.5 水泥，单方用量380，改进以后呢使用32.5水泥，掺26%粉煤灰。从节约资金角度说，因节约了大量水泥而节省了工程费用300多万元。从碳减排的角度来说，因节约大量水泥而减少了碳排放，大概26%。再谈谈化学外加剂。化学外加剂呢是现代混凝土中最重要的组分，作用很大，用量很小。也正因为用量小，在混凝土碳排放计算的时候，常常被忽略不计。这里呢，我想特别强调一下，参加碱水剂十分有益于混凝土减排。参加混凝土碱水剂的作用效果，在不改变原配合比的时候，可以大幅度提高混凝土的流变性和可塑性。如果碱水可以提高各龄期混凝土的强度20%到80%，如果保持强度，就可以减少水泥的用量15%到30%。这个呢，就是它减碳作用的原因。关于碱水剂今后发展方向，建议呢，关注开发生物质碱水剂，以减少化学外加剂对石化资源的依赖和消耗。目前呢，已经有一些生物质的碱水剂，比如木质素磺酸盐碱水剂，它的原料呢就是造纸行业的废液。另外呢，淀粉基碱水剂，它的原料呢是玉米淀粉、土豆淀粉等等这些。这张图片呢是中国建筑材料研究总院研发的一种淀粉基碱水剂，它的示意图，利用淀粉加工出呢贝塔环弧晶，通过点滴化学把它接支到聚羧酸碱水剂的侧链上。由于呢贝塔环弧晶具有很大的一个空间位主，可以显著的提高呢聚羧酸碱水剂的分散性能和保摊性能。减碳的路径2是优化混凝土生产工艺，减少能源消耗。这里呢，我列了4个具体的措施。我呢想重点谈谈第2点，大流动度混凝土和第4点，3D 打印混凝土。 先谈谈大流动度混凝土。混凝土大流动度以后呢，可以减少振动和泵送等等能源。但是如果遇到炎热高温的天气，长距离运输，或者因为交通堵塞导致运输时间过长等等，这些特殊情况下，要保持混凝土大流动度就是一个难题。如果发生塌落度损失过大，就会泵送困难，甚至堵管。所以呢，开发高温条件下高保摊型聚缩酸碱水机非常重要。这个目标呢，可以通过对塑形共居物分子结构的设计来实现。根据所用水泥4大矿物表面电荷电性的不同和它吸附量的差异，设计侧链的组成和密度，调整外加剂的吸附行为，就可以实现2个小时甚至更长时间的保摊的效果。这是一个例子，采用3种不同的主链侧链连接方式，可以制得子型、醚型、显亚胺型的聚缩酸碱水剂。那么我们从右图呢可以看到，同样的参量下，显亚胺型聚缩酸碱水剂它的保塌效果呢是最好的。这是另外一个例子，是2种不同侧链的聚缩酸碱水剂，其中一个侧链中间呢引入了丙烯酸羟乙酯，通过酯键的水解实现了2个小时流动度的保持，比常规侧链聚缩酸碱水剂和耐系碱水剂呢具有更好的摊落度保持能力。3D 打印混凝土，这是混凝土圈子近期的一个热词。国内外很多的科研单位呢都在开展这方面的研究。3D 打印是基于计算机模型，通过连续组成叠加材料来生成3维实体的技术，又称为呢真材制造。3D 打印的本质，它是一个制造过程。这个制造过程的特点是无模具，生产周期短。相比于现有的混凝土制品需要钢模生产和高温养护，3D 打印工艺它是减碳的。3D 打印技术已经用作房屋人行桥的建造，尽管呢目前它的示范意义还是大于它的实用意义。3D 打印技术和装备是有很多种的，这几个动画呢分别展示了分层打印、D-shape 工艺、挤出成型轮廓工艺和智能动态浇筑工艺。目前呢，在中国使用最多的是挤出成型轮廓工艺。中国建筑材料科学研究总院呢，也开展了3D 打印方面的研究工作，重点的方向呢有3个。寒冷条件下水泥基材料3D 打印技术研究的目标呢，是未来在极地和月球这些寒冷的环境下完成无人化施工建造房屋。3D 打印直径混凝土技术，我们的目标呢是要做结构的3D 混凝土构建，同时呢提高它的承接粘接强度。3D 打印城市雕塑和市政小品，这是我们打印的一个雕塑，名字叫对话。左边呢是我们中国古代喝白酒用的一种容器，叫爵。右边呢是一个更西方、更现代的喝葡萄酒用的玻璃杯，中间呢用12根不锈钢管连接，寓意呢是通过古今中外世纪不断的交流和沟通，世界的文明在传承和发展。这是我们打印的一个城市街边小品，名字叫喵屋。这是给城市流浪猫一个温暖的家。这是一个组合构件，中间是小猫的家，可以放一些保温材料在里面，上面呢种花种草，草丛里面呢有猫食盘和水碗。让我们回到混凝土减排的途径3，提高混凝土耐久性，延长使用寿命。钢筋混凝土结构造价低，是土木工程设计的首选，但从世界范围看，钢筋混凝土材料并不像人们以为的那样耐久，一些服役不到30年就出现了破坏。世界范围看呢，每年用于工程维护和修复的费用高达数千亿美元。延长混凝土寿命并不是一件容易的事情，因为呢，混凝土使用过程中间需要抵抗各种内部和外部因素造成的破坏，比如说海水绿岩引起钢筋锈蚀，潮湿环境下混凝土发生碱固料反应， 寒区混凝土动容循环破坏、盐卤地区硫酸盐侵蚀，这些都会影响混凝土的寿命。近年来呢，混凝土的设计理论、材料性能和施工水平在进步，重要工程的设计寿命也延长至100年。延长混凝土结构的寿命也是中国碳减排的重要路径，因为节省了巨额的维护、拆除和重建。混凝土工程服役年限延长1倍，减少的材料消耗，包括水泥是惊人的，保守估计要达到20%到30%。这里呢，我介绍2个与延长混凝土寿命有关的研究工作的信息。首先是严酷环境下长寿命混凝土技术。通过研究呢，我们发现在严酷环境条件下，水泥基材料的水化产物和微观结构会发生更大变化。严酷环境呢，是指高浓度多离子的海水或者盐卤环境、高辐照以及它引起的高温环境，还有高原地区的低气压、低温、大温差、冻融等等这些。在这些因素作用下呢，水泥水化产物会发生变异和失稳，比如说 CSH 凝胶它的聚合度发生变化，氢氧化钙呢反应分解，钙矾石晶型转换，水分呢发生脱附和分解。水化产物变异就会引起混凝土孔隙率增大，连通孔增多，微结构劣化。混凝土呢就表现出溶蚀、膨胀、开裂、剥落、强度损失等等。因此呢，严酷环境下长寿命混凝土技术更需要被关注。中国呢地域辽阔，混凝土工程正在向严酷环境地区拓展，每年呢约有1亿立方米混凝土施工。4年前，国家科技部立项开展了极端环境下混凝土长寿命理论和技术的研究，如今呢刚刚结题，项目呢开发了新材料，突破了共性关键技术，提出了性能表征新方法，开展了工程示范应用，实现了原定的目标。项目呢已经发表论文150多篇，都标注有项目资助号，大家呢在期刊杂志上都可以看到，所以呢这里我就不详细介绍了。第2个长寿命混凝土研究信息呢是关于自修复混凝土的。济南大学周宗辉教授团队研究了混凝土的本征自愈合，发现有水的时候呢，混凝土中间未水化的水泥颗粒会参与到自愈合的过程，在裂缝中间继续水化，生成水化产物。自愈合以后，裂缝开口处的这个碳酸钙沉淀逐渐就覆盖了原有的水化产物。他们呢深入研究了水泥的矿物组成、细度、混合材等等因素对本征自愈合能力的影响，给出了水泥质量控制的建议，非常的有价值。武汉理工大学于建英教授团队呢，他们是研究了多元离子络合型自修复混凝土，利用外加4%到6%的络合剂，促进裂缝处碳酸钙的生成，提高呢混凝土的自修复能力。他们研发的多元离子络合剂的优点呢是络合离子的数量多、品种多，络合物迁移的速度快，在寒冷和海洋环境下呢，修复能力强。这里呢，给大家展示一下它们自修复的效果。参加多元离子络合物的混凝土呢，能自修复宽度为0.35毫米的裂缝。梯裂的参加有络合剂的混凝土，经水养护几天以后呢，测得混凝土的渗水率降到了0。这个呢是在海水中的自修复效果。络合剂呢也可以使0.34毫米宽的这个裂缝自愈合。裂缝处自修复的产物呢，经过分析是碳酸钙和氢氧化镁，这个镁呢来自于海水。在一些艰险山区建成的大型混凝土工程中间，有些重点部位是难以进行维护和维修的，使用自修复混凝土技术就可以增加安全的保障。最后呢是混凝土减碳路径4，就是利用混凝土碳化进行碳捕集与利用。经典的混凝土耐久性理论认为呢，研究混凝土碳化反应是因为碳化反应降低混凝土碱度，引起钢筋锈蚀破坏，还有呢，碳化反应会造成混凝土收缩大、易开裂， 所以呢，我们一直关注如何避免和减少碳化反应的发生。现在呢，要利用混凝土碳化反应进行碳捕集，就是要反向利用碳化反应。混凝土发生碳化反应需要先扩散进入混凝土内部，再与其中可碳化的物质，氢氧化钙呀、CSH 凝胶啊这些物质发生化学反应。试验结果显示呢，碳化反应的速度受到湿度和二氧化碳浓度的影响。湿度为60%的时候呢，二氧化碳扩散的速度，还有呢二氧化碳反应的速度都比较快。这呢也是大多数加速碳化试验方法中间把相对湿度参数确定在55%到65%的原因。二氧化碳浓度越高，被吸收的二氧化碳就越多。20%二氧化碳浓度的时候，除了氢氧化钙以外，我们发现呢 CSH 凝胶等物质也参与到碳化反应。这个呢就启示我们，混凝土的碳化反应真的是一种潜在的可以进行碳捕集的手段。2020年，美国纽约的 Solidia 这个公司，它的 CEO Tom 宣布呢，他们公司的产品 Solidia 水泥和 Solidia Concrete 都可以把混凝土呢变为地球的碳汇，也就是说，他们产品消耗二氧化碳量大于生产过程中间排放二氧化碳的量。我们来看一下 Solidia 水泥的碳减排。烧成温度呢由1350度降低到1200度，石灰石用量减少，加上燃料减少，生产1吨水泥可以减少碳排放250公斤，这样就减了30%的碳。再来看一下 Solidia 混凝土碳减排，它的原理呢是用二氧化碳代替水与水泥呢发生反应，完成固化。制品呢在养护固化过程中间，二氧化碳呢与水泥塑料发生化学反应，捕获碳，生成的碳酸钙呢把骨料粘在一起形成混凝土。每吨水泥呢消耗二氧化碳高达300公斤，这个过程呢大概减碳40%。所以 Solidia 公司呢综合水泥生产减排二氧化碳的30%和养护固化过程中间消耗二氧化碳40%， CEO Tom 就宣布70%的减碳，很有价值，很创新的一项工作，祝贺他。根据网络资料呢，用这种水泥制备混凝土工艺和常规工艺是一样的。这个公司生产的混凝土道面砖直接铺设到纽约警察局消防车通道上，来证实它的强度和耐磨性呢很好。预拌混凝土施工现场呢是无法使用二氧化碳气体的，需要呢把它用固体或者液体的形式引入到混凝土中间。这个公司呢正在和其他公司合作，把废的二氧化碳气体转化成草酸或者柠檬酸，用酸与水泥发生反应，可以捕获4倍量的碳，生产负碳混凝土。前景呢非常可观。OK。今天呢，和大家一起分享了助力碳减排的4项混凝土技术新途径。在准备 PPT 过程中呢，我对碳减排的认识在加深，感想也是很多的。那么最后呢，总结成2句话和大家分享：科技减排任重道远，全球水泥和混凝土市场很大，绝对值得我们脑洞大开，认真思考，用创新的技术和产品助力碳减排。谢谢各位，欢迎讨论和交流。嗨。
That's all from Dr. Wang. Thank you very much. Now I would like to take this opportunity to introduce our partner, FutureBuilt. FutureBuilt is the world's largest sustainable building materials exhibition and the largest exhibition in the British building material industry. FutureBuilt has been held since 2005, and its main purpose is to showcase the industry's most advanced environmental protection technology, gather top decision makers, and promote the industry's low carbon development. The next Future Build will happen from the 1st of March, 2022 to the 3rd of March. There's still spaces right now, and they're going fast. If you're interested in exhibiting, please contact Marina Stewart via the email or just go on Future Build's website at futurebuild.co.uk. Once again, allow me to remind audience on Zoom, please use the chat box to post questions and comments for the Q&A session. And you can also scan the QR code on top to join our WeChat group or the bottom for our LinkedIn group to continue the discussion. Now let's watch the presentation from Dr. Sayed Ghaffar on low carbon concrete for modern methods of construction.
Hello everyone, it's an immense pleasure to have the opportunity to present to you low carbon concrete for modern methods of construction. My name is Dr. Sayed Ghaffar, and hopefully we find the topic today interesting. Before I start to go into the details of my talk, just a little bit background of where I come from and what is my background. So I am an associate professor at Brunel University, London, which is situated, you can see on the map here, in west of London. We have around 15,000 students and over 2,000 academic staff. Our turnover last year was £240 million, and we are a higher education research institute, and we are very research intensive. Of course, our university is named after Brunel, who was a great engineer at this time, and he made great contribution to the Industrial Revolution in the United Kingdom. A little bit about myself. I'm an associate professor, as I said, in the Department of Civil and Environmental Engineering. I'm a chartered civil engineer. I am also a member of the Institute of Concrete Technology and a fellow of Higher Education Academy. Back in 2017, I established this research center or research group called AMTC, Additive Manufacturing Technology and Construction. I have 2 postdoctoral research associates and a couple of PhD students active in this research center. In the past, I've been involved in 8 different R&D projects, totaling a value of £6 million. My sponsors have been Engineering and Physical Sciences Research Council, British Council, and European Commission. And I try with my research, I try to focus and cover a variety of construction materials with a focus on developing low carbon technologies. I try to combine the material science research area with innovative technologies such as 3D printing, which is actually the main focus of today's talk. I also act as an associate editor of for the Journal of Results in Engineering, which is published by Elsevier, and also Structures and Buildings, which is published by Institution of Civil Engineers. My research focuses on contributing to 17 Sustainable Development Goals, which are set by the United Nations back in 2015, in the hope to transform our world by 2030 to achieve all the sustainability and sustainable goals. My focus is specifically on number 11 and number 12, so sustainable cities and communities and responsible consumption and production. And today I will tell you how I try to achieve the aims of these goals. Before we do that, I just try to set the scene and show you the research significance by giving you some facts, which are a little bit scary, in fact, actually. So we start off with CO2 emissions in the UK. 47% of all the UK CO2 emissions are linked to the construction and operation of the built environment. So this is a very scary fact. The other one is that the construction industry generates about 35% of the waste to landfill across the globe. Again, something needs to happen here, and we need to move towards circularity within the construction industry. And also another fact is that according to IPCC and UNEP, the building sector consumes 40% of the total energy use and accounts for a third of energy-related carbon emissions. Concrete produces 550 kilograms of CO2 per cubic meter used. Obviously, I will be talking about concrete and how we can eliminate the use of Portland cement within the concrete. And the main ingredient, which is Portland cement, is responsible for about 8% of global CO2 emissions. I will introduce some of our mixed formulations for the concrete that has zero Portland cement. Another important fact that really highlights the importance of circularity within our industry is the fact that nearly half of all the materials extracted from the earth annually are used in concrete. The extraction of construction virgin aggregates is the main global non-metallic mineral construction, 41% gravel and 31% sand, which is approximately 5 gigatons annually. So these are just some of the important facts, and they need our attention, they need investment, they need stakeholder collaboration and external industry engagement. Together, we should try to come up with solutions for such scary and concerning facts. So let me just quickly introduce AMTC. So the focus of our work is on material science. Obviously, we try to 3D print, and 3D printing is the underpinning technology within our group. But 3D printing is not something very futuristic anyway. It's just a combination of several disciplines together, such as control, software, mechanical, electrical. But the main area of science that needs attention is the material science, and how we can combine different waste streams into a material that can be printed, that can be used for such a technology in order to be able to transfer our success stories from other industries to the construction industry in a hope to revolutionize the construction sector. Because other industries, of course, have used 3D printing very much successfully, and they are implementing this technology for the benefit of their industries. Examples are biomedical industry, automotive industry, aerospace industry. But in the construction, the technology is still in its infancy, and it needs a lot more attention and investment in order to be able to reach its true potential. Excuse me. So the main aim of my research is to introduce automation and digital technologies to the conservative construction industry and into construction processes. We are focusing on valorizing construction and demolition waste, so how can we recover resources from aggregates, from concrete, for example, how can we recover aggregates for remanufacturing of concrete from demolition waste? And it requires us to combine material science and innovative technologies in order to achieve the circular economy goals of sustainable development. So today I will be talking about low carbon concrete for modern methods of construction, and I will go into details, the material science details of how we've been able to prove that this technology can actually help us to obtain something which has good mechanical properties and can be used for structural load-bearing components within the construction industry. Before we get into that, I just want to show you the complexity that we are dealing with. So 3D printing, additive manufacturing is a multi-parameter complex scenario. You need to optimize the printer itself, the printing environment, the robotic system that you're using, the gantry system that you may be using, the pump pressure, the nozzle size, the geometry. Then you also have the printable feedstock, so the printable raw materials, the concrete in this case. What is the actual composition of this concrete? What is the aggregate size? What is the characteristics of the concrete that is being printed? And on the other hand, you have the geometry. Obviously, we know that one of the main advantages of 3D printing is that it allows us to realize complex geometries. We don't really have to stick to the boxes and circles anymore. We can have these curvatures, corrugated walls, and these important parameters need to be optimized before we can realize the full potential of 3D printing. And they all work hand in hand So the optimization of all these parameters takes a long way. It needs a very detailed plan and dedication for each of these main areas. So the printer, the geometry, and the principle for feedstock. There are obviously more smaller areas that need attention when it comes to additive manufacturing. So this is just a picture to show that we started and how the preliminary testing allowed us to actually achieve a full printing. We started by just a mortar gun, printing different layers, only one layer actually, to see the open time, to see the to investigate the rheological properties of the cement. The printer that we use is a very small printer. The reason why it's small is because we want to print many objects and we're just trying to optimize the mixed formulation. Later on, we can just easily transfer that to a much bigger printer and start printing building blocks. But at the moment, we're just trying to focus and optimize the material formulation. As I said, the aim is to combine different waste streams into this 3D printable material. So you can see our nozzle here, you can see the extruder system. Also, all of it has been designed by our group, and we haven't purchased anything off the shelf. Everything that you see here has been put together thanks to my research and design research groups. Again, this shows our study program. We started by focusing on the extruder design. How can we design appropriate nozzle? Proper prototyping was extremely important. We had plenty of trial and error in order to get it right. And also the other focus was on the mixture design and how we can optimize the fresh properties so that they are ready to be extruded, to be printed, and to have that shape stability. So we done tests on the bendability, on the mechanical strength, and different sizes of nozzle. You can see that if we found out that when we use a smaller nozzle, 10 millimeter, for instance, the printability and extrudability is not adequate. So the sizes that are good enough for 3D printed of mortar or 3D printed concrete is 15 millimeter circular nozzle and 20 millimeter circular nozzles. Now here I want to talk about our original paper that was published last year or this year, beginning of this year. We looked at how we can come up with a mixed formulation of cementitious composite that do not have any potent cement. So we looked at geopolymers. Of course, everybody knows that geopolymers are alternative. They use alternative cementitious materials such as fly ash, which is an industrial byproduct, GGBS, another industrial byproduct from the steel manufacturing, and silica fume. And how can we activate them so that they have that cementing property? So we use sodium silicate and sodium hydroxide. And here we can see that initially we had 6 different mixed formulations. You can see all the mixed formulations here. We selected the best performing one in terms of printability and in terms of mechanical strength, which was mix 4. And we decided to add some nano functional materials, in this case, nanographite plastics. The reason why we did that is because we wanted to see how much further we can take the mechanical strength and what is the effect that these nano functional materials can have in order to improve not only the fresh properties, not only the printability, the extrudability, but most importantly, the mechanical strength of these objects, of these 3D printed building blocks. So we decided to add very small percentages, 0.1, 0.3, 0.5, and 1% of nanographite into our mixes in order to assess the mechanical improvement and mechanical enhancement. So this here shows our testing program. As I said, we had 6 different mixes. On those 6 mixes, we carried out fresh properties, hardening properties, so flexural strength, the compressive strength. We assessed the bendability, the extrudability, and out of these 6, we have 2 mixes that performed really well. So, namely, mix number 3 and mix number 4. Again, on those 2 mixes, we carried out some more testing, some more rheological evaluation in order to select the best one, which was mix number 4. And then we took that and we added nanographite in 4 different dosages, and we carried out investigation again of these new formulations. So the results are here. I start with fresh properties. You can see This is an important element, an important parameter to investigate, which is called flowability. So how easy is it for this cementitious mixes to flow after it's been agitated 15 times? All the tests, of course, have been carried out according to European standards and or American standards. You can see an image of mix 1, which is at the very stiff end of the scale, and mix 6, on the other hand, was flowing way too much than we required to for a 3D printing application. And mix 4, shown in green, had the best flowability after 15 minutes. It was very consistent, and this shows the suitability of this mix for 3D printing application. Another assessment that we had in terms of buildability when it was fresh and the concrete was just being set, and before it's set into a hardened state, we looked at the first layer height reduction. So the first layer that is being deposited in a 3D printing process, and how the weight of subsequent layers reduce the initial height of the first layer. This is important. Why? Because it helps us to investigate and evaluate the buildability when it comes to large-scale components. And you can see that after 15 layers or even 10 layers, this reduction was stopped, and we were not seeing that much reduction in terms of millimeters in the height of the first layer. It shows that the first layer was already set. It was strong enough to sustain the weight of subsequent layers. So this is a very good result and something that we were hoping for. So we were able to achieve that. And now we obviously looked at the bar properties, the mechanical strength and density. You can see PM stands for printed mix 4. It has a flexural strength of around 8. Also, the casted specimen was also evaluated for the comparative reasons. The casted sample had slightly higher by about 2 MPa, 2 megapascal higher flexural strength. But what was interesting is when we add 0.5% of nanographite or 1% of nanographite, that mechanical strength, the flexural strength, actually increases quite significantly. And this is extremely positive when it comes to enhancing the overall mechanical performance. So the same observation or the same trend was observed in the compressive strength, where in this case, 0.1% of nanographite had a significant enhancement of compression. But these values are very encouraging, especially in compression. We know that the concrete, especially geopolymer, is quite strong, but the problem was the flexural strength. And here you can see with the addition of nanographite, you're able to increase the flexural strength. And the density didn't show that much difference between the printed and the casted sample, but the addition of nanographite improves or increases the density. It leads to a denser cementitious composite, and it's quite understandable because these nanoparticles, they are able to fulfill all the micropores and nanopores within the microstructure of these cementitious composites. So this was an unexpected observation. And here we can look at the scanning electron microscopy, and in order to basically explain why the flexural strength has increased once we have added the nanographite. We looked at the microstructure of the failed position after the flexural strength within that prismatic sample, within that cubic sample, and we observed that the graphite, the nanographite, is actually bridging the crack, and this is why it takes a lot longer stress to break the sample compared to a sample that does not contain any nanographites. So the second study that here I'm presenting was on the use of PVA fibers in order to see what is the effect of fibers in terms of enhancing the mechanical performance. And we also looked at another nano functional material called attapulgite nanoclay. We used the same supplementary cementitious composite, the same industrial byproducts such as fly ash, GDBS, and silica film, in the same percentages as before, the same activated sodium silicate and sodium hydroxide, and the same sand aggregate size. But this time, instead of adding nanographite in different ratios, we added PVA in 2 different ratios. So the PVA fiber of in the ratio of 0.25% and 0.5%. And at apologite, 0.5% and 1%. And also we wanted to have a hybrid combination between the fibers and the nanoclay functional materials in order to assess the mechanical and the fresh properties. So here you can see the testing program. We have additives, we have different binders. We came up with 6 different formulations. We started looking at the fresh properties, durability, mini-slump durability. The casted composite were subject to mechanical property assessment and microstructure assessment. And the 3D printed composites are also subjected to the same assessments. So in the results here, you can see that the density of the printed sample this time is a lot higher than the casted samples. The reason is because we have fibers now and we have nanoclay and apologite. In the process of the extrusion, the hopper design and the nozzle design aligns all the fibers, and we see a lot less cavities, a lot less voids within the sample, and that's why the density is a lot higher. The flexural strength performance of the samples that have fibers is a lot more than the samples that did not have any fibers. The CS stands for control sample, so the sample that does not contain any additive. And you can see here that 0.25% of fibers has actually improved the flexural strength quite significantly. And these are the printed samples that we tested for bending performance and flexural strength. And the compressive strength results are showing the same trend. So very encouraging results overall. And this is just some pictures showing 4 different samples. A is the control sample that does not have any additive, no fibers or no nano-functional materials. And B is a sample with functional materials. C is a sample with only apologite and no fibers. And D is the hybrid sample. So it contains nanoclay and PVA fibers. We also obviously looked at the microstructure of the specimens after failure, after they were subjected to a flexural test. Again, we can explain the high flexural strength of the samples with PVA fibers by looking at the microstructure. And you can see that the cracks have been bridged by these fibers. It shows that it takes a lot more stress in order to break that sample compared to a control sample that does not contain any fibers. So these are just additional information that proves the mechanical observations. So currently I have one project which started very recently on digital fabrication and integration of material reuse. And the aim is to 3D print building blocks that are a lot more environmentally friendly. We received funding from the European Commission. The project will end in 2024. The main work package here is again on mix optimization, but this time we are using a lot more various different waste streams. So we are even looking at rubber waste, we are looking at agricultural waste, different type of fibers, different type of carbon-based materials, and how we can incorporate them into our base mix formulation, which does not contain any Portland cement, and it is purely made by a combination of several supplementary cementitious materials and industrial byproducts. Obviously, then we have to do the standard work packages such as the testing and validation and evaluation of different properties, fresh properties and other. The main focus, obviously, another focus of this project, let's say, is to show that circular construction actually can work if we have a systematic strategy in place. So the underpinning strategy here is the 4R framework. So we try to reduce the waste by using additive manufacturing, by using 3D printing process. Reusing of waste is also another important element to this framework. Recycling, selecting the most appropriate process for recycling, for example, concrete waste into aggregate, so that we can remanufacture concrete again from a waste-driven product, from a waste concrete, for instance. And recovery is all about the end of life and how much, what is the best percentage, let's say, or yield of getting resources, secondary recovered materials from chunk of concrete or any other stream of demolition waste. So we try to focus on demolition waste in this project, and we are trying to get all of our raw materials from construction demolition waste sources. So this model here is, it tries to explain, but obviously circular construction is a lot more complex than this model can show. But I have tried to be brief and try to introduce the main areas, the main subtopics of circular construction and how we can actually achieve circularity within construction. So you can, if you're interested, you can read this paper later on, but it starts from waste identification and source separation. Is extremely important to make sure that we are able to identify before we carry out the demolition of the project. So the complete demolition is not good enough anymore. We need to have smart dismantling in place. For that smart dismantling, we need to have pre-demolition audits. We need to use robotics. They are a lot more efficient. We need to use AI, clever sensing technology, clever separation technologies, move on to mobile on-site operations. The remanufacturing process on-site or off-site prefabricated elements are all part of circular construction, and they need to be addressed. They need, all the challenges within these topics needs to be addressed before we can completely achieve circularity within construction industry. Then one of the other main challenges which requires the policymakers and the governments to be involved is the quality management and certification. We need to have rules and regulations for testing new materials that are coming from waste-driven products. So you can find a lot more information if you're interested on this topic in my paper here. So in the future, we hope to develop 3D printable construction materials for sustainable manufacturing. This sustainable manufacturing, of course, is additive manufacturing and 3D printing. We are hoping to valorize or add value to waste through integration of the waste in construction materials. And ultimately, our vision is to reduce CO2 impact of concrete components by 70 to 100%. So I really thank you for your time and attention, and I'll be happy to answer your questions. Please do get in touch with me if you have any questions. Thank you.
Okay, all right. Thank you, everyone. Thank you for the expert presentations. That's wonderful. We're aware that there might be a glitch due to the internet issue, so we apologize for the inconvenience, and a recording will be uploaded on our website later so you can catch up on the missed content. We can see now all three experts are live on Zoom. Dr. Sui might join us later. Let's now give time to our Q&A coordinator, Xiaoyan, because she has been monitoring and organizing questions from both platforms throughout the webinar. And now she will feedback these questions to our experts. We'll give translation after experts' answer is finished, so to guarantee the quality of translation. Xiaoyan is on you now.
先会问一下各位专家另外一个问题吧，就是说之前我们听说过一项实验是把生蚝的壳磨碎再烧制，然后因为生蚝的消耗也很大，不知道各位专家对其他生物质在水泥混凝土的使用有没有什么经验呢？那个王教授先回答一下这个问题。
就是贝壳烧了以后是吧？
对，就说我们目前有没有其他生物质在水泥混凝土的使用上我们有没有什么经验呢？
生物质的材料呢，把它煅烧以后，是可以来用作这个水泥混凝土中间来做参和料来使的。煅烧以后呢，刚才我们那个教授也都说了，主要是看它有没有活性。如果呢它有硅质材料，它如果能够被水泥水化的氢氧化钙来激发它这个潜在的活性的话，那么呢它是可以呢对强度是有利的。
如果它本身是惰性的材料，比如说我们直接把它研磨以后呢，实际上它是一种惰性的填料。如果能够磨到一定的细度以后呢，实际上它对于强度也是有好处的啊。
好的，谢谢王教授。那不知道赛义德博士对于这个问题有没有什么见解呢？
Yeah, I mean, we have used natural fibers in order to reinforce the cementitious composite, either the concrete or the mortar. In terms of using it as a supplementary cementitious material, so the ash of biomass, we haven't done any work on that, but we've done a lot of work on natural fibers in the other projects, which is called Grow to Build. We looked at fibers like hemp, jute, wheat straw, wood fiber, and we looked at how we can use these fibers as reinforcement for concrete and other cementitious materials. We have actually done some 3D printing of concrete that has wheat straw as a biomass fiber in order to improve the tensile strength, the ductility, and the flexural strength of the concrete.
请那个胡安博士回答一下刚才这个问题。
Right, with oyster shells, what we obtain is mainly lime, right? So this is part that you can use as cement, right? But using biomass, there is the possibility to obtain different compositions. So it depends on the type of biomass that we burn. So there is the possibility to work with wood, and different types of wood will bring to different solutions with ash, because it depends on the chemical composition that you obtain with it. It is important to find solutions in which we obtain high levels of silicium and low levels of calcium. So in this case, it is in which we can obtain a silica material, a siliceous material that can be used with a combination for a replacement of cement. So that's the best option that we can have. So it can be wood, it can be any other types of bio waste that we can obtain, for example, from agriculture, or any other type of waste from municipal waste, for example, or any other types of waste. The problem that we can have is the composition that we obtain at the end, right? There are problems, for example, with heavy metals. So if we burn municipal waste, for example, we can get contamination with heavy metals, and in that case, it's not useful for concrete. So we should decontaminate it first. So it depends. It depends on the solution, and every biomass that we use has a different application. That's so it is not a unique solution that we can find. There are different solutions, and it depends on the biomass that we have.
好，谢谢胡安博士。那么接下来我们想请问一下赛义德博士，纳米材料生产的碳足迹高吗？
So these nanomaterials are carbon-based. We haven't done any study on the life cycle analysis yet. One question that we always get using these nanofunctional materials is the cost. But I can confirm that the initial cost is slightly higher. Now there are companies in Italy, especially called Nanosite, and they are producing industrial scale nanofunctional materials which are not that expensive. The point that we are trying to make here is that the initial capital cost of using these nanofunctional materials might be high, but their benefit in terms of improving the durability, in terms of improving the mechanical strength and the physical strength of these cementitious composite is a lot more, and it outweighs the initial cost. of course, the initial cost is there because we are talking about functional materials in the size of nano. But the benefits that they bring in terms of the long-term benefits, it's worth the investment. But in terms of, to answer your original question, we haven't done any life cycle analysis on these carbon-based materials that are in the form of nano.
好，谢谢赛义的博士。接下来我们想请问一下隋教授，目前我国水泥窑烧煤比例是多少呢？是否都要改为天然气或者用电？这种改造企业能否承受呢？
实际上目前来说，用天然气，如果把这个现在中国水泥现在作为水泥熟料的煅烧，主要是用煤的这样的一个燃料换成这个天然气的话，这个从经济上来说呢是难以承受的。所以说真正的要实行减排，或者说将来实现这个碳中和的话，原料替代，如果是利用这个天然气来去替代的话，也包括利用所谓叫氯氢来替代的话，实际上还是有很长的路要走。
好，谢谢隋教授。不知道王教授对于这个问题有没有什么补充呢？
我也觉得哈，这个碳减排，现在呢引起了各方的高度的重视，但是呢，实际上我们在生产工艺方面呢，还要进行很大的调整，特别是在水泥的这个方面，水泥的这个能源的一个变化，对任何一个行业，对任何一个国家来说，能源的变化，就是我们由原来的燃煤变成天然气或者是氯氢，应该说中间还有很多的细节，包括设备，包括工艺，都要进行很多的探索，在这些比较细致的研究的基础上，我觉得应该进行一些放大的工业试验以后，才能进入到行业的规模化生产。相比之下呢，那么一些材料组成方面的调整，现在呢进展比较大一些，不管是水泥的成分的调整，还是混凝土组成的这个调整，这方面呢，相比于能源的变革都要进步的快一些。
好，谢谢王教授。那么接下来我们想问一下胡安博士，您的报告中提到应用稻壳灰、废弃塑料、天然植物到水泥混凝土中，在欧洲是否已经有成熟的应用，还是说是处于研究阶段呢？
It is still in the field of research. There are some experiences to develop. Sorry. There are some experiences to develop, for example, to create any type of paints in which we can have waterproof properties. And there are also experiences to mix these biopolymers in concrete mixes, and they are made waterproof. So these are the experiences that we have until now. And another thing that we can see is that with these biopolymers, we can increase a bit mechanical strength of this concrete. So these are the experiences that we have until now. There are big advances, for example, in Mexico, using nopal, a type of cactus, right? And with these experiences, what they are getting is good solutions with concrete and mortars. They are using, for example, for rendering, mortars that are waterproof, mainly for facades or other type of solutions that we can have with rendering mortars. So these are the experiences that we are getting now with these biopolymers. As I said, this is a big field to explore. We've got a tradition. So in our tradition, we have used many times grease, blood, any other biopolymers that we have mixed with clay and earth, and we have made houses, huts in history. So this is a good binder that we can explore. But at the moment we haven't gone to this field as much as we should in science. So this is what we are doing until now. Until now, it is taking plants. We are taking the biopolymers from these plants, mainly cacti, and trying to use this as a binder. So this is the experiences that we are doing now.
好的，谢谢胡安博士。那接下来这个问题想请问一下4位专家，目前替代水泥的工业固废的碳排放值是怎么计算的？有没有像水泥一样的统计值做参考呢？首先请那个赛义的博士回答一下这个问题。
Yeah, so we are trying to increase the percentage of fly ash incorporated into our binder, but we will have, only, let's say, 10 years supply of fly ash. We need to find alternative eco binders, let's call it. In terms of increasing it, the problem we have is the hydration reaction and the strengthening mechanism. So we will not be able to get good, strong composite, cementitious composite, if we increase the percentages of fly ash. On the other hand, the activation of using sodium silicate or sodium hydroxide, the activation of these binders is not sort of industrially feasible, let's say. We can, and we have done some research on one-part geopolymer, which means we use powder activators, and we just add water to the fly ash or GGBS from the Slug. The problem, as I said, is the supply chain, but one of the issues or one of the points that the researchers or engineers in the UK are actually making is that we have a 10-year supply of fly ash. Let's use it, and then later on, we will think about alternative. Especially, I was talking to some engineers on the HS2 project, High Speed 2 project, and there are a lot of joint ventures who are involved in this project, and they want to make it environmentally friendly solution in everything they do, in all the temporary works, tunneling, reinforcements. They have a very strong view that they should use all the fly ash available to them in the UK. And if that supply finishes, then we think of alternatives. So at the moment, there is a strong push for using fly ash and finishing it up, let's say. And then later on, they will look for alternative eco binders. But as I said, scientifically, if you want to develop a cementitious composite entirely from fly ash, that is not possible. The reason is because the mechanical strength of that resultant concrete is not up to a good standard at all. You need to have some other binders such as GGBS or silica fume to give it that strength that it needs, especially at early ages.
好，谢谢赛义的博士。接下来想请隋教授回答一下这个问题。
好，是这样的，就是利用水泥生产过程当中来去用固废来替代，来去生产水泥的话，实际上这个问题呢涉及到2个方面。第一个方面呢，我们说利用固废来去替代熟料，来在最后的环节生产水泥。当然，那个前面王教授说的，它也可以放到混凝土里边去替代水泥，来去做混凝土。当然，从水泥的角度来说，第一个方面体现在用固废来替代熟料来生产低碳水泥，这是第一个方面。第二个方面是涉及到用这个固废来替代原料，而且如果从二氧化碳减排的角度来说，主要是替代钙质原料才能去 从方法学的角度能够体现出对这个整个生产过程当中，尤其是熟料生产过程当中，它的这个二氧化碳的直接排放的下降。实际上是这个问题呢，固废替代，实际上是在这个水泥生产过程当中，我们要分2个方面来去解释。在这个用固废来替代熟料生产低碳水泥这个方面，在我的那个报告里，实际上已经是应该是比较清楚的讲了这个问题。我其中呢有一个简单的一个估算的办法，就是我们假设我们目前来说，我们单位熟料的二氧化碳的直接排放，比如说我们现在说是 0.85 吨二氧化碳每吨熟料的话，那么中国水泥目前来说呢，我们的熟料系数是 0.66。那我们简单的来去判断的话，那么就是把这2个数一相乘，那么就 0.66 乘以 0.85 大概等于 0.56 这样一个水平。那实际上就得出了单位的水泥的直接二氧化碳的直接排放的强度，这实际上就是可以给出这样的一个计算方法。还有一个第一个方面呢，如果是钙质原料的替代的话，假设我们利用电释渣，主要成分是氢氧化钙来替代二氧化碳的话，来替代这个钙质原料石灰石的话，那么按照方法学来去，这个要按照整个目前标准，无论是这个国际上的这个方法学的标准，还是中国标准里面，可以重新来去计算整个替代原料钙质原料过程当中，那么它的碳排放是多少？这样的话我们会重新来去计算。所以呢，它涉及到问题的2个方面。没有了。
好，谢谢隋教授。那接下来请王教授回答一下这个问题。
OK， 水泥的刚才隋院长他已经跟大家解释了，我呢就从混凝土的这一块利用我们这些工业废渣呢来解释一下。混凝土中间呢，利用这些工业废渣，我们如果来评价它的碳减排呢，基本上是2个方面。一个呢就是它在混凝土中间替代水泥用量，另外一个呢就是从它改变混凝土的那个工艺中间的能耗。从替代第一个方面来说呢，替代掉多少水泥，我们通常呢就说按照它替代掉的水泥就生产过程中间的能耗，我们呢就认为它是多少。比如说它替代了 30%， 我们呢就是粗略的估算，我们就说有 30% 的一个替代，这个是从材料组成上。另外一个呢就是从工艺上，工艺上呢比较麻烦一点，因为混凝土呢它是分预拌混凝土和预制混凝土。如果对于预拌混凝土呢，它主要就是搅拌振动，但是呢对于预制混凝土来说呢，它还有一个养护，那么热养护的过程中间的能耗呢其实是比较大的。这样的话呢，我们加进去的这些工业废渣，它本身节约下来的呢就不如能耗。讨论工业废渣它在减碳方面的作用呢，我觉得应该区分一下它用在哪一种类型的混凝土中间。目前呢在中国关于预拌混凝土它的那个就是单方混凝土中间碳的排放已经呢有了标准，就是预拌混凝土碳排放量计算已经有了标准。但是呢预制混凝土这一块因为呢每一个工厂它的那个热养护制度差别比较大，所以呢这一块暂时呢还没有我还没有见到这个标准，大家呢后面可以来探讨一下。
好，谢谢王教授。那么接下来请胡安博士回答一下这个问题。
Right. The standards that we have, it is the same standards. We are working with life cycle assessment. So these are the standards that we have. We have for all materials, and there are no difference. The only thing is I think this person was talking about emissions with waste. When we are considering emissions about waste, the thing is that we need to calculate the carbon emissions that we have to take this waste to landfill, okay? But we should also consider the carbon emissions that we will have in future to recover this waste, because in future we are delaying this problem for future generations. So it is not just to take this waste to landfill, it is also to consider carbon emissions that we will have to recover this waste in 20, 30 years, right? Because this is what they will have to do in 20, 30 years. We cannot leave it this way. So when we calculate carbon emissions about waste, we should add them up, right? So it is one consideration that we need to take for this. So every waste that we produce, they have a lot of carbon emissions embedded in them, right? Because it is all this process that goes beyond the life cycle of this waste. Okay, so calculating the carbon footprint, it should include also this process beyond the life cycle of this waste, and also how to recirculate this in the economy again, right? So how to recirculate it in the new life that we are going to give to this waste. I think she was also talking about precast elements. And yes, I agree that there are issues. For example, if we are using alkali activation, probably we will have to use heat in the process. It is not a large amount of heat, so it will be about 60, 70 degrees that it will be in the early stages of this concrete. So we are consuming energy there, right? But of course, this is not as much as an energy as if we produce cement, because when we produce cement, we need to heat it at 1400s, 1600s degrees, right? So it is not the same amount of energy that we can that we have to consume. So that's the difference that we have to do. So we have to compare different solutions, different materials, different embedded carbon footprints, and with it is the way that we can understand if we are increasing the environmental impact or not. Another thing is cost, of course, and how we can adapt it to our manufacturing process. This is another question, and this is another problem, another issue. I understand that it is not easy, so it is a process. It is a process in which we are going to optimize our manufacturing processes, and we are going to make them every time more efficient as long as we learn and as long as we grow in this process, because this is a process. We are all learning and improving as much as possible in this process.
谢谢胡安博士。那么接下来我们是今天的最后一个问题了，想请问一下胡安博士，除了文章中提出的粉煤灰和高炉炉渣等工业固废替代部分水泥外，其他行业如有色金属工业等，像铝灰等材料在替代水泥的前景如何？
Right. The main thing it is to see how this waste or these byproducts are produced and the composition that they have, right? So the good point with iron, with steel, it is the combination that they have with carbon. So with coal. So they are the process that we have. It is that they are made with coal. So the fuel that we use is coke in the case of steel. And what happens is that the combination, the chemical composition that we get for this slag is specifically according to the ferrous and carbon composition that we get. So this is the main point of blast furnace slag, that we get from this manufacturing process. Regarding aluminium, I don't think you have this combination. So probably it's not possible to use it. And with other metals, it depends on the manufacturing process and the composition, the chemical composition that we get for these byproducts.
That marks the end of our Q&A session. Thank you everyone for staying with us. We have so many more questions that we didn't get to ask, but we will try to coordinate these questions to our speakers and then feedback to our audience. Please scan the QR code on top to join our WeChat group or on the bottom for our LinkedIn group to continue the discussion. Please follow our next webinar session on low carbon applications of wheat straw building materials on the 20th of October at 9 a.m. British Summer Time. Last but not least, the recorded video of today's session will be uploaded on our website. So thank you very much, and I look forward to seeing you next time. Bye, everyone. Thank you.
Thank you and bye.
Thank you very much. Bye.